Welcome back to another video. Today we're going to look at classifying PDEs as elliptic, parabolic, or hyperbolic. So this comes into importance when later on, if you ever get into learning method of characteristics. This is a big determination of whether you should use separation of variables or method of characteristics to solve the PDE. This is very helpful in numerical solutions. It's also very helpful in like a mixed problem. Like for example, potential flow. If the flow is, remember we used the Laplace equation for potential flow. If the flow is subsonic, you end up with an elliptic PDE, and if it's supersonic, you end up with a hyperbolic PDE. That leads to different solutions for the same general equation, depending on flow conditions. So things change. So it's very important to be able to classify it, to be able to determine what method you need to use to solve the PDE. It can be helpful in that. So it's more of like an application kind of helper, like for higher level stuff. But what we have here is the general case for the second order PDE, linear, where we have a uxx, 2b uxy, c uyy. Those are the coefficients, and this is our definition for what's called the discriminant. This is what determines if the solution is parabolic, hyperbolic, or elliptic. Now you might see this as defined differently than what I have here. It varies depending on who your instructor is, where you find it, the textbook. It can vary. It can be just all A, B, C, no 2 in there. This doesn't exist. This could be B squared minus 4AC. I think I've seen it like that. It just depends. But so let's start with the heat equation. Which is, now for this equation, we replace y with t. That's our second variable, right? This is an equation of two variables, t being our second one. But you can see here that term is first order, so we just kind of ignore it. Imagine it's 0. Looking at our general form, a is alpha squared, b is 0, c is 0. So our discriminant is alpha squared times 0 minus 0 squared, which is equal to 0. So our solution is parabolic. So the heat equation is parabolic. Now let's look at the wave equation. So the wave equation is alpha squared the uxx is equal to utt. We're going to move that over. Our a is alpha squared, our b is 0, our c is negative 1, right? Looking at this, c is negative 1, b, we don't have any of these terms, we only have this and this. So this is pretty simple, right? This is just going to be alpha squared times negative 1 minus 0 squared, that is negative alpha squared, which is less than 0. Let's take a look. If it's less than 0, it is hyperbolic. So the wave equation is hyperbolic. What about the Laplace equation? we're going to look at the 2D steady Laplace equation, right? Time independent. That's the one we've been looking at. That is uxx plus uyy equals 0. We have a is 1, c is 1, b is 0. That is 1 times 1 minus 0. That's 1, which is greater than 0. If it's greater than 0, it is elliptic. The 2D steady Laplace equation is elliptic. Now, so those are, the ones we've been working with. Let's look at some other, crazier examples. So one example I have is uxx plus 2uxy plus uyy equals 0. So for this case, our a is 1, our b is 1. Remember, because it's 1, right? Because the definition is 2b uxy. So b is 1, right? The 2 doesn't change anything here. And our c is 1. So everything's 1. So our discriminant is just 1 times 1 minus 1 squared, which is 0. If it's 0, it is parabolic. Let's take a look at another example. I have one more. Oh, this is an interesting one. So we have x uxx minus y uxy equals 0. So our a is x. Our b, now, you see we don't have the 2 there, so what we're going to have to do is divide by 2, so it matches our general equation. Our c is 0. The discriminant is x times 0 minus negative y over 2 squared. That is negative y squared over 4, which is less than 0. So now, so this is a different kind of situation we have here. So what we're going to say is for all values of y, because it is squared, this PDE is hyperbolic. And for y equals 0, this PDE is parabolic. See, this one changes. This is just like Laplace equation for potential flow, where the term will differ based on subsonic or supersonic flow. Kind of the same thing. So yeah, this PDE will depend on what y is. So that's the end of classification. This might be the end of my PDE series. I might do a video on the ambiguous solution for the wave equation. And I might do one on Laplace transformations. I mean, not Laplace, Fourier transformations. And maybe method of characteristics. But that's the end of this video. Hope you enjoyed. See ya.